Imagine sitting across from a machine and having a conversation so natural, so insightful, so creative that you forget you're talking to software. Now imagine that same machine can turn around and design a nuclear reactor, compose a symphony, prove a mathematical theorem, perform surgery, write legal briefs, and teach kindergarten, all with equal mastery. That's artificial general intelligence, and it represents perhaps the most consequential technology humans will ever create. The AI systems we use today are impressive but fundamentally limited. They're specialists. A system that plays chess brilliantly can't drive a car. A language model that writes eloquently can't design buildings. These are examples of narrow AI systems trained for specific tasks that can't transfer their knowledge to new domains. They're tools, sophisticated ones, but tools nonetheless. AGI is different. It's an intelligence that can learn, reason, and adapt across any domain, just as humans do. Think about what makes human intelligence special. You can learn to cook breakfast, then use those same cognitive abilities to understand philosophy, repair a bicycle, comfort a friend, or plan a vacation. You transfer knowledge between domains, you reason by analogy, you learn from just a few examples, you understand context and nuance. AGI would possess all these capabilities, but without human limitations, no need for sleep, perfect memory, the ability to think at speeds limited only by processing power, and potentially capacity to improve its own intelligence. The timeline for AGI remains uncertain, with predictions ranging from a decade to a century, but the trajectory is clear. Every year, AI systems accomplish tasks that experts previously thought were decades away. Systems now engage in reasoning that was considered uniquely human just years ago. The gap between narrow AI and general intelligence is closing, not through magic, but through better algorithms, more computational power, and deeper understanding of how intelligence works. When AGI arrives, it won't just be another technology added to our toolkit. It will be a multiplier on every other technology. Scientific research accelerates exponentially because AGI can formulate hypotheses, design experiments, analyze results, and iterate at superhuman speed. Medical diagnosis becomes perfect because AGI can instantly access all medical literature and compare a patient's symptoms against every known case. Education transforms because every student gets a teacher with infinite patience and perfect knowledge of their learning style. But the implications cut deeper than productivity gains. AGI forces us to confront fundamental questions about human purpose and identity. For all of history, humans have been the most intelligent entities on Earth. We've built civilizations, created art, explored nature, and pondered existence. What happens when we're no longer unique in these capacities? When machines can do everything we can do, but better and faster, what role remains for humanity? The control problem looms large. An AGI optimizing for seemingly benign goals might pursue them in ways that harm humanity, not out of malice, but because we failed to specify our values precisely enough. An AGI trying to cure cancer might conduct unethical experiments. One asked to make people happy might drug everyone. The challenge isn't making AGI intelligent, it's making it aligned with human values and keeping it that way as it potentially modifies its own code. We're building something that could be the best thing ever to happen to humanity, or the last thing we ever build. The outcome depends entirely on getting the development right. Take the most powerful supercomputer on Earth and give it a problem. Simulate the behavior of a moderately complex molecule, say protein with a few hundred atoms. That supercomputer might churn away for weeks or months, tracking every quantum interaction, every electron probability cloud, every force between particles. Now, give that same problem to a quantum computer. It could solve it in minutes, maybe seconds. That's not an incremental improvement. That's a different universe of computational power. Classical computers, the ones we've used since the 1940s, process information as bits, tiny switches that are either on or off, 1 or 0. Every calculation, no matter how complex, breaks down into billions of these binary operations happening in sequence or parallel. It's remarkably effective, which is why classical computers have transformed civilization. But there are problems where this approach hits a wall, problems so complex that even if you converted every atom in the universe into a classical processor, you still couldn't solve them before the heat death of the cosmos. Quantum computers work differently at the most fundamental level. Instead of bits, they use quantum bits, qubits. These exploit one of the strangest phenomena in physics, superposition. A qubit doesn't have to be 1 or 0. It can be both simultaneously, existing in a probabilistic state until you measure it. Even weirder, qubits can be entangled, meaning the state of one instantly correlates with the state of another, regardless of distance. These quantum properties allow quantum computers to explore multiple solutions to a problem simultaneously. Think of it like searching for a specific book in a vast library. A classical computer walks down every aisle, checks every shelf, examines every book in sequence. It's thorough but time-consuming. A quantum computer, through superposition, examines all the books simultaneously, collapsing to the answer when measured. For certain classes of problems, optimization, simulation, cryptography, this parallel processing power is revolutionary. Drug discovery provides a perfect example. When pharmaceutical companies develop new medicines, they need to understand how potential drug molecules will interact with target proteins in the body. These interactions are quantum mechanical events, electrons forming or breaking bonds, molecular shapes shifting. Simulating this on classical computers requires brutal approximations. We basically guess, then test in the lab. It takes over a decade and billions of dollars to bring a new drug to market, largely because we can't accurately predict molecular behavior. Quantum computers can simulate quantum systems naturally because they operate on the same principles. They could predict exactly how a drug candidate will bind to a protein, what side effects might occur, which modifications would improve effectiveness. The drug discovery timeline could collapse from 15 years to 15 months. Similar revolutions await materials science, battery chemistry, catalyst design anywhere quantum mechanics matters. Then there's cryptography. Most of our digital security relies on mathematical problems that are easy to create but nearly impossible to reverse. Like multiplying two huge prime numbers is simple, but factoring the result back into those primes is astronomically difficult for classical computers. Quantum computers using Shor's algorithm could crack these encryption schemes easily, rendering most current internet security obsolete overnight. But quantum computers aren't magic. They're not better at everything. They won't make your web browser faster or improve video game graphics. They're specialized for specific problem types. The engineering challenges are immense too. Qubits are incredibly fragile, disrupted by the slightest vibration or temperature fluctuation. Current quantum computers require cooling to near absolute zero and operate in isolation from any interference. Yet we're making progress. Companies and research institutions have built quantum computers with dozens of qubits and are pushing toward hundreds. We're approaching quantum advantage, the point where quantum computers definitively outperform classical ones for practical problems, not just laboratory demonstrations. Close your eyes and imagine moving your arm. Now imagine that thought, that neural signal traveling from your brain, could control a robotic limb, a computer cursor, or even communicate directly with another person's brain. This isn't hypothetical. It's happening in laboratories right now. Brain-computer interfaces are dissolving the barrier between thought and action, between mind and machine, opening possibilities that challenge our very understanding of what it means to be human. Your brain operates through electrical signals. Roughly 86 billion neurons fire in patterns, creating cascades of electrochemical impulses that generate everything you experience: every sensation, emotion, memory, and decision. For decades, we've been able to measure this activity crudely using EEG sensors on the scalp. But recent advances allow us to read and even write neural signals with unprecedented precision. The most immediate applications target medical restoration. Consider someone paralyzed from the neck down after a spinal cord injury. Their brain still generates the signals to move. Those commands just can't reach the muscles anymore. Brain-computer interfaces can intercept those signals directly from the motor cortex and translate them into movement commands for robotic limbs or exoskeletons. Patients who haven't moved in years can now control prosthetic arms with their thoughts, picking up objects, even feeling texture through sensors that send signals back to the brain. We're restoring other lost functions too. Cochlear implants already bypass damaged ears, sending audio signals directly to auditory nerves. Retinal implants are giving limited vision to the blind by stimulating the optic nerve. People with locked-in syndrome, fully conscious but completely paralyzed, can now communicate by thinking letters that appear on a screen. Each of these represents a direct bridge between technology and the nervous system. But the technology is pushing far beyond medical restoration. Researchers have achieved brain communication in experiments where one person's thought triggers an action in another person's brain through linked interfaces. Imagine the implications: thoughts transmitted directly without the messy translation into words. Perfect communication of complex ideas and emotions. A teacher could share not just information, but the actual experience of understanding a concept. Memory enhancement comes next. We're beginning to understand the neural codes for memory formation. Interfaces could potentially strengthen memories, helping people with Alzheimer's or age-related cognitive decline. Or they might allow memory augmentation in healthy people, perfect recall of everything you've experienced, or even the ability to save and load memories like computer files. The enhancement possibilities extend to cognition itself. Direct brain interfaces to computational systems could give you instant access to information without searching. Think of a question and receive the answer as naturally as recalling your own memory. Mathematical calculations performed by external processors feeding results directly to your neural networks. Learning accelerated by directly stimulating the right neural pathways in the right sequence. This technology also presents unsettling scenarios. If thoughts can be read, what happens to privacy? If memories can be written, what's real and what's implanted? If cognition can be enhanced, do we create a cognitive divide between those with access and those without? When you can back up and restore your neural patterns, are you still the same person? If two brains link directly, where does one consciousness end and another begin? The engineering challenges remain formidable. The brain is vastly complex, with connections numbering in the hundreds of trillions. Current interfaces read or stimulate thousands of neurons at best. We need millions for true high-fidelity brain-computer communication. The skull presents both an engineering barrier and a safety feature. Non-invasive methods lack precision. Invasive methods risk infection and tissue damage. Yet progress accelerates. Within decades, brain-computer interfaces might be as common as smartphones, augmenting human capability in ways we're only beginning to imagine. Every second, the sun converts 4 million tons of matter into pure energy through nuclear fusion. That process has been running for 6 billion years and will continue for another 5 billion, producing more energy than human civilization could consume in millions of lifetimes. For nearly a century, scientists have dreamed of recreating that stellar alchemy here on Earth. We're finally on the verge of making it work. Fusion is the opposite of the nuclear fission we've used since the 1950s. Fission splits heavy atoms like uranium, releasing energy but also creating dangerous radioactive waste that remains hazardous for thousands of years. Fusion does the reverse. It squeezes light atoms together, forcing them to combine. Specifically, isotopes of hydrogen, deuterium and tritium merge to form helium, releasing enormous amounts of energy in the process. It's the same reaction that powers every star in the universe. The fuel availability alone makes fusion transformative. Deuterium can be extracted from ordinary seawater. There's enough in Earth's oceans to power human civilization at current consumption levels for billions of years. Tritium is rarer, but we can breed it from lithium, which is abundant in Earth's crust. Unlike uranium or plutonium, these materials aren't weapons grade. Unlike fossil fuels, they don't produce carbon emissions. The primary waste product is helium, an inert gas we use for party balloons. But there's a catch that's kept fusion perpetually 30 years away for the past 70 years. To make atoms fuse, you need to overcome their natural electromagnetic repulsion. Protons carry positive charges, and positive charges repel each other violently. Only at extreme temperatures around 100 million degrees Celsius, several times hotter than the sun's core, do atoms move fast enough to smash through this barrier and fuse. At those temperatures, matter exists as plasma, a state where electrons strip away from atoms entirely. You can't contain plasma in any physical container. It would instantly vaporize any material. The solution involves using powerful magnetic fields to suspend the plasma in a vacuum, never touching the walls. The most promising design, called a tokamak, uses magnetic fields in a donut shape to contain and compress the plasma. Other approaches use lasers to compress fuel pellets, creating fusion through sheer pressure rather than sustained containment. The challenge has always been energy balance. Heating plasma to fusion temperatures requires enormous energy input. For decades, fusion reactions consumed more energy than they produced, scientifically interesting but practically useless. That changed recently. In December 2022, researchers at the National Ignition Facility achieved fusion ignition, a reaction that produced more energy than was delivered to the fuel capsule. It wasn't yet net positive for the whole system, but it crossed a critical threshold that proves the concept works. Commercial fusion reactors could be operational by the 2040s. Imagine the implications cascading through civilization. Energy becomes functionally unlimited and clean. Climate change mitigation becomes vastly easier when we can power carbon capture systems without worrying about energy costs. Desalination of seawater becomes trivially cheap, solving water scarcity. Energy-intensive processes like aluminum smelting or hydrogen production for fuel cells become economically viable everywhere. Developing nations wouldn't need to build massive solar or wind farms or rely on fossil fuel imports. A single fusion plant could power entire regions. Space exploration transforms when spacecraft can carry compact fusion reactors, enabling faster propulsion and eliminating the need for solar panels or radioactive thermal generators. Fusion doesn't just provide clean energy, it provides energy abundance, and abundance changes everything. Poverty diminishes when the fundamental constraint on industrial civilization disappears. The question isn't whether fusion will work, but whether we'll perfect it before climate change forces more desperate measures. Look at the double helix structure of DNA. That elegant twisted ladder contains the complete instruction manual for building and operating a human being. For most of history, those instructions were fixed, unchangeable, passed down with only the random variations of natural mutation. Then in 2012, scientists demonstrated CRISPR, a tool borrowed from bacterial immune systems that acts like molecular scissors, cutting DNA at precise locations and allowing us to delete, replace, or insert genetic sequences. We can now edit the code of life itself. The immediate applications target genetic diseases, conditions caused by specific errors in DNA that we can now correct. Sickle cell anemia results from a single letter change in the gene for hemoglobin. CRISPR can fix that error in patients' blood cells, potentially curing a disease that has caused immeasurable suffering. Muscular dystrophy, cystic fibrosis, Huntington's disease. Thousands of genetic conditions could become treatable or even preventable by correcting the underlying genetic cause rather than just managing symptoms. Cancer treatment transforms when we can edit immune cells to better recognize and destroy tumors. CAR-T therapy already does this, reprogramming patients' T cells to hunt cancer. Gene editing makes this faster, more precise, and applicable to more cancer types. We're approaching the ability to make someone's immune system specifically target their unique cancer. But biotechnology extends far beyond fixing problems. We can engineer crops that resist drought, require less fertilizer, or produce higher yields, potentially feeding billions more people. Bacteria can be programmed to manufacture insulin, spider silk proteins, or biofuels. Mosquitoes engineered to be resistant to malaria parasites could save hundreds of thousands of lives annually. The ethical dimensions loom large. Germline editing changes made to embryos that pass to future generations crosses into territory that makes many uncomfortable. Editing genes to cure disease seems justifiable, but what about enhancement, increased intelligence, athletic ability, longevity? We're approaching capabilities that could let us guide our own evolution, redesigning humanity itself. The technology is powerful enough to eliminate genetic diseases or create unprecedented inequality, cure suffering, or enable dangerous experiments. We have the tools. The question is whether we have the wisdom to use them responsibly. Imagine a solar panel floating in geostationary orbit 35,000 kilometers above Earth, bathed in constant, unfiltered sunlight. No clouds block it, no night interrupts it. The sun's energy hits it at full intensity, 24 hours a day, 365 days a year. This panel converts that sunlight to electricity, then beams it down to Earth as microwaves, where ground stations receive it and feed it into the power grid. This is space-based solar power, and it could solve humanity's energy crisis permanently. The math is compelling. Solar panels in space receive about 10 times more energy than panels on Earth's surface. The atmosphere absorbs and scatters roughly half the sun's energy before it reaches the ground. Weather blocks more. And of course, Half the planet is always in darkness. Space has none of these limitations. A single square kilometer of solar panels in orbit, properly positioned, could generate gigawatts of continuous power, enough to supply a major city. The technology for every component already exists. We know how to build solar panels, how to convert electricity to microwaves, and how to receive those microwaves safely on the ground. The receiving stations, called rectennas, would be large but relatively simple arrays of antennas that convert microwave energy back to electricity. The microwaves pass harmlessly through clouds and atmosphere, and at the power densities involved, they're safe for birds, planes, and anything else that might pass through the beam. What's changed is launch costs. For decades, space-based solar power remained impractical because launching the necessary mass into orbit cost too much. But reusable rockets have dropped launch costs by factors of 10, and they're still falling. Orbital construction techniques are improving. Within 20 years, we could have the first commercial-scale space solar stations. The implications reach beyond just clean energy. Developing nations could receive abundant power without building massive ground infrastructure. Disaster zones could get emergency power beamed from space. Remote areas, polar research stations, islands, anywhere difficult to reach could have unlimited electricity. And unlike ground-based solar or wind, space solar provides consistent baseload power, not intermittent generation requiring massive battery storage. Energy becomes a service delivered wirelessly from orbit. Walk into a factory today and you'll see robotic arms welding car frames, machines assembling electronics, automated systems moving products from station to station. These robots are impressive but fundamentally limited. They perform pre-programmed motions in controlled environments, repeating the same actions endlessly. They can't adapt to unexpected situations, can't learn new tasks easily, and certainly can't navigate the messy, unpredictable environments humans move through daily. That's changing rapidly. The next generation of autonomous systems combines advanced artificial intelligence with sophisticated sensors and mechanical design to create machines that can operate independently in complex, unstructured environments. We're seeing robots with genuine dexterity, mechanical hands that can manipulate delicate objects, tie knots, and adjust their grip based on tactile feedback. Humanoid robots that can walk across uneven terrain, climb stairs, recover from being pushed, even do backflips. More importantly, these systems can learn. Show a modern robot how to perform a task a few times, and it extracts the underlying pattern, adapting the motion to new situations. Machine learning allows robots to improve through experience, developing skills the way humans do through practice and feedback rather than explicit programming. The applications span every industry. Construction sites could use robots for dangerous tasks like high-altitude work or handling hazardous materials. Warehouses are already deploying mobile robots that navigate autonomously, but future versions will handle complex picking and packing without human intervention. Agriculture could employ robots for harvesting delicate crops, identifying ripe produce through vision systems, and picking it with appropriate gentleness. Elderly care presents both opportunity and necessity as populations age. Robots could assist with mobility, remind patients about medications, provide companionship, and alert human caregivers to emergencies. Search and rescue operations could send robots into collapsed buildings or disaster zones too dangerous for human first responders. The labor market implications are unavoidable. Any repetitive physical task could eventually be automated. But this also means humans can focus on work requiring creativity, empathy, and complex judgment qualities that remain distinctly human, at least for now.